Well, hello everyone. Welcome back to Adrian's Digital Basement. We're back to the Plexus P20. This is going to be part 4 in this series on this multi-user Unix workstation from 1985. If you haven't seen the previous parts, I recommend you watch them in order. There'll be links in the description below to all of those parts. And as usual, I'll be continuing off where we left off in part 3. Now, as a recap, I was recently given this machine, and because there was absolutely no documentation or, well, any information about it whatsoever, except for one single brochure that was on BitSavers, I decided to start part 1 off by taking it apart and really digging into all the constituent parts on this machine. I dumped the ROMs, I dumped the hard drive image, and then in part 2, I actually went to figure out if I could power this up. So I had to service those power supplies in here, there are 2, and I got it actually turned on. And then in part 3, I hooked the hard drive back up, the original hard drive I might add, and actually was able to get this thing booted up into Unix. So this thing was actually working. But unfortunately, that success was short-lived, and the machine quickly developed a fault and would no longer boot. And that has brought us up to where we are now with this machine in part 4. So in this video, I want to try to get this machine working again. And well, there's been some really interesting developments around this computer, especially around community help with me trying to fix this thing. So without further ado, let's get right to it. So where we left off in the last part, there were 2 major faults in this system. The first was the power supply, which is connected to the motherboard here, and it's behind the motherboard. It actually has the reset circuit for the motherboard in it. It's a bit unusual, I hadn't seen that personally, but the key switch here, which has a reset position, actually grounds a pin on the power connector here that goes to the power supply. Inside the power supply is a circuit that, I don't know, takes that input and also checks against voltage rails and power good and stuff like that. And then it outputs a reset signal to the motherboard. What happened when the power supply reset circuit failed is that it was constantly leaving the computer in a state of reset. It never brought it out of reset, which is bringing that pin there for up to 5 volts. I showed that with the oscilloscope, and it was just stuck. Also in part 2, when this thing was boot looping, that was clearly the reset circuit that was inside the power supply, resetting the machine over and over again. And while I didn't catch that on the oscilloscope, I did see that eventually in part 3, although not on camera. But then it failed altogether, and now all it does is stay in reset. So I gotta solve that problem, because what I was doing in part 3 to get this computer to even try to boot was I was manually just using a resistor to bring this thing out of reset by pulling the reset signal on this chip here, which used to come from the power supply, but I cut the trace up to 5 volts. Once I did that, the system would start executing and all was good. And then the other big fault with this computer is an actual showstopper where the system fails its diagnostics and goes into a halt state. That gives us an error code, which I still don't quite know what it means, but if we're going to try to investigate any of that stuff, I need to first sort out this reset problem that's happening here with the power supply. Now, it goes without saying that I can obviously just open up the power supply and, well, try to figure out the reset circuit that's in there, and that should get that circuit fixed. But I have to say, when I was in the power supply multiple times in the previous parts, I noticed that there were several ICs inside there that obviously make up some voltage comparators, there's some overcurrent protection stuff, and some other things that I think all lead to the reset circuit essentially keeping this motherboard in reset to, I don't know, try to protect it, or so you know there's some kind of fault. The power supply also does shut down, because I did see that in, I think it was part 2, when there were some problems with the capacitors. I noticed the 5 volts from the power supply would just disappear altogether, which was obviously that voltage protection stuff happening, probably because some voltage was going out of spec because of the excessive ripple. Now, it goes without saying that opening the power supply and trying to troubleshoot that thing is probably the right thing to do, but is it the thing I'm going to do right now? No, it's not. I want to get away from using the whole resistor stuff that I was doing in part 3, and I'm going to make something new that's just going to drive the reset circuit on the motherboard and do it in a way that I can control it, so I'm not relying on a faulty power supply circuit to do it, and then we have better control of the system. I talked to my friend Frank about coming up with a new reset circuit, and he actually recommended that the reset circuit in the original PET 2001 is a very solid circuit. It uses a 555 timer and a few little components around there, and this would actually be a really good way to implement a reset circuit that would work on this machine. And in fact, when I was inside the power supply, I did notice that there was a 556 timer IC in there that is obviously part of the reset circuit. So to replace it with something like a 555 from the PET wouldn't be that bad a deal, and I could obviously just put a little tiny perf board or something stuck around here and connect that to the motherboard and we'd be good to go. Now, as great as the 555 timer is, this is 2024, and there's actually something that I can use that's a little bit easier to do, and it gives me some software control of things, and it's this, an Arduino Uno. I have a box full of these things. I haven't used these things in ages, and that's because, you know, they're a little outdated at this point. I think these have, been out for like 10 years now at least. But the great things about this is that they run on 5 volts. It's really easy to implement. I can do software control, so if I need to do additional stuff for debugging purposes, like say keep toggling the reset circuit continually, I can do that really easily with this. And if I get this system working and it comes time to making the reset circuit work properly, I can do one of two things. I can try to fix the power supply again, or I could just get like an AT Tiny, and I have a bunch of those, or just a tiny single chip implementation of what you see here with only a few IO pins. And that's enough to basically hook up to this front switch right here to have the reset input and essentially control the whole reset circuit with a microcontroller, and it would work perfectly fine. So what I did is I whipped up a quick sketch for this thing. It's very simple. All it does is when this thing gets powered up, it waits 1 second and then it brings pin 2 out of reset, pulls it up to 5 volts. I'll just connect that back to the reset line like I was doing in part 3 through a resistor, mind you. I don't want to hook the 5 volts of this directly up to this circuit in case something goes wrong here. And I added an extra little feature that if I plug a jumper link like this between pin 3 and ground, what that will do is it will continually reset the system every, I think I had it set for 20 seconds. And obviously I can plug this into the computer to change that timeout if I need a different value. And the reason why I implemented this constant reset thing is if this thing runs its diagnostic and then it fails, I want it to just restart itself. And I want to keep doing that so that I can start probing around on the motherboard looking for faults, and the system will keep running the diagnostic. As it was before, it does the diagnostic once, halts, and then that's that. I would have to turn this computer off and on, or turn this to the reset position if I hook this signal back up to this Arduino, for instance. So why bother with that? Well, let's just do it in an automated fashion. First thing I need to do is just hook this thing up to this computer and let's power this thing up. It's been a little bit of time since I worked on part 3, and let's see if this thing is absolutely still broken and fails that diagnostic test. There's the Arduino. I have it hooked up to 5 volts on the power supply connector, and then I have it hooked up to the reset input pin on the clock chip here, and that just feeds the entire reset circuit, and that's going through an 800 ohm resistor, which is what I was using last time. That seemed to work. As far as the state of the rest of this thing, I actually have all the various other components unplugged from the power supply, so only the motherboard is connected. The SCSI cable is connected here, but let's just get that off of here. We don't actually need that for this first test. I do also have this multi-bus expansion chassis connected, but that second power supply, I've actually never powered it up or tested it. It's not connected to this. So that resistor board is installed in here, but that doesn't do anything. That is actually just for the power rails to burn extra power if you're using that second power supply and you don't have any multi-bus cards installed. This machine supports up to 3 additional multi-bus cards, and I think cards that they intended you to use with this thing were additional serial ports up to 8, and then Ethernet board, and I think there was another communication processor type board. Anyhow, it's time to power this up. We know that when it goes into the failed state, the second LED here, which you can just see the back of, will flash. And let's turn this on, see if this comes out of reset. There we go, came right out of reset, just like that. I think this means I should get the serial cable plugged into it so we can at least see what's happening on the computer over there. So the serial cable is connected, and I'm not really getting anything on putty here. So what I need to do is put that jumper link on the Arduino between pin 3 and ground, which should restart the computer, and then we can hopefully see at least the Plexus banner. Okay. I put the jumper in place. As you can see, it is now running the self-test. Okay, same exact error we had before. So, oh, look at there, it's rebooting again. So that's great, that works. Alrighty, yes, I think the code has a 10-second delay. And yes, there it is right there, delay 10,000, so waits 10 seconds, which is actually a good amount of time. I could probably shorten that a little bit because this self-test seems to fail so quickly. And then, well, it helps me poke around a little bit more. Since the Arduino was a success, I decided to get rid of that, and I loaded that same code onto an AT Tiny 25 and I soldered it directly onto the board. Well, it's actually in a little socket. That means I can remove it if I need to change the code on it, like to add extra functionality or whatnot. But this little chip does the exact same thing the Arduino does, which basically fixes the reset circuit. All I need to do to complete this is wire up the output of this switch here that when you turn it to the reset position, it actually just grounds one of the signals here, which used to go to the power supply connector. And I'll just wire that directly to the ATtiny here. It has internal pull-up resistors for the inputs, which is enabled. So all I need to do is ground that pin, and then, well, we're off to the races. I can either have the code do the reboot cycle like we have now, or I can change it to just reset the machine until you put it back to the run position, which is the original configuration. So where are we right now? Well, let's be honest, that reset problem, that was low-hanging fruit and actually very easy to fix, which is a little bit of a hardware problem. The bigger problem is, how do we get this computer booting again? Let's think about an IBM PC BIOS. It has similar diagnostic codes that can fail when you first power on the machine. Because the BIOS is really well understood and all of those codes are documented, if you get a code when you first turn that machine on and it just halts, well, you could just look up what the code means, and if it tells you there's a problem with, say, the keyboard controller, well, you know where to focus your attention on the motherboard. Now, even if you didn't have schematics for the motherboard, typically the keyboard circuit is relatively easy to understand because, of course, the keyboard plugs into the back and you can just look at the traces and they'll go to one of the chips on the board and you can go backwards from there. But with this computer, we have a couple really big issues. The first is we have no idea what any of those diagnostic codes mean. The code we're getting is 4F02. What does that refer to? Who knows? But even if we did know, how do we know what part of the motherboard is the problem? Now, if it was something simple like a ROM checksum, okay, well, we know where the ROMs are and we can just, I don't know, try to swap those out or whatever. But if the code is pointing to some type of a logic fault on the motherboard, well, take a look at the board. There's a ton of logic on it, and lots of the logic has been condensed into PAL chips, programmable array logic. And there are, I think, 8 of those PAL chips on the board, and one PAL chip can take the place of a whole ton of TTL logic ICs. And that means those PALs sort of obfuscate a lot of the functionality that would otherwise be laid bare by TTL logic chips because you could just look up what they do, and that's all hidden away inside PAL chips. So at the end of part 3, when this thing broke, I was honestly feeling a little despondent. Looking at this board, it's just a huge unknown mass of chips. There are 6 layers to the PCB. That means you cannot just look at traces running around the board because they often go to a via and then go to an inner layer. You don't really see where it goes. That means if you have a chip that you suspect is bad, like let's pick this one down here, to figure out where all of the pins go on this, you have to essentially clip onto one of the pins, say pin 2, and then touch every single pin on every single other chip on the board. Well, you could skip the VCC and ground pin, which are usually 2 obvious pins. And then you have to write down every single pin that has continuity to that chip. You write down the chip number, the pin number, and then you have to go through and reiterate that process through every other pin except for the ground and the VCC. What that's called when you have a pin on one chip that goes to a pin on a bunch of other chips, it's called a net. And when you're designing PCBs, you have these things called nets, which essentially have a name, and then it has a list of every chip and every pin that those signals go to. And you can imagine that there's actually traces running around the board everywhere that go to all these various components. It can also go to resistors and diodes and other types of passive components on the board as well. But really, to start to reverse engineer the functionality of the board, you have to go through that entire process. It can be a little more difficult as well if you have a board that has actually suffered some damage, like battery leakage, because it can eat through traces and it can do that on inner layers as well that you might not realize. So when you're figuring out the nets of the chip here going to every other pin on the board, you might miss some stuff because that connection is already broken. Unless you have a board that is 100% operational and has no damage, you can't be 100% sure that you're not missing stuff. This board also has all sorts of bodge wires, which means you have to make sure you take those into account as well, because clearly some traces have probably been cut, definitely some pins have been lifted to install these bodge wires. So that right there is one of the first barriers to try to figure out how a board like this works. Now, when you do reverse engineering on a system like this, you have to do it methodically, where you would say, start from the clock circuit. And there's a crystal oscillator up here, and there's another one down there. So we have at least 2 clock circuits on here, and you start to trace that out. Typically, those clock circuits will get divided down by some logic, and then those clock signals will make their way all over the board. You can then start from things like the CPUs, because we know what all of the pins on the CPU do, address bus, data bus, stuff like that. You can start figuring out those nets to unravel the mysteries of the board. There are other parts of the board that are obvious about what their function is. There's a connector right here that goes to the RAM board on the back, so we know there's data and address bus signals that go to that. We have some static RAM chips right here that probably provide some amount of memory that the computer or the processors can use during operation of the system. But there's also a bunch of static RAM over here, which is used for most likely a different type of function. This is much faster static RAM than the stuff that's over here. So this stuff is probably used for a memory mapper function, which has to do with protected memory and virtual memory that needs to be implemented to properly implement a Unix system. There are also these 74-154 chips right here. There's 3 of these, and these are almost always used for select logic on various motherboards. So you can start to tone out the nets that are connected to that to try to figure out what peripherals and whatnot are selected by these chips. Probably things like the serial ports over here, and the RAM and ROMs and stuff like that. So familiarity with the way these types of systems are typically designed helps a little bit in just trying to figure out the fundamental blocks and areas of this system. But when you look at this area right here, it's just a whole ton of TTL logic. And some of this is going to be built for implementing the SCSI. Some of it's going to be select logic for, say, the serial ports. But a whole lot of this stuff around here is probably used for the memory mapper function, which is that virtual memory thing I talked about that uses this SRAM. And it's not really easy to tell with this system where those chunks of the board are. Like the mapper stuff might be all located right here around the SRAM, but it might not be. It might be over here too and over here, and it's really hard to say. Now, the reason why I'm talking about all this is because, as I mentioned, this is only half of the problem. Understanding how the board works and the nets and the schematics or the lack thereof, that is solvable by a whole ton of work. The other half of the problem is understanding the diagnostic routine that's running and to see what is it doing when it fails. That would give us the clue of where on the board we could focus attention to try to get this thing working. Now for me, hardware, like doing the reverse analysis of the motherboard, is time consuming, but it's totally something I can do. But understanding how 68,000 code works or 6810 code works in these ROMs to unravel the mysteries of that diagnostic error code, that is way above my head. So at the end of part 3, I was just feeling pretty despondent because, well, initially when that happened, I just thought, how am I ever going to figure out what these error codes are? I'm never going to be able to do that, at least on my own. So I was talking on the phone to David over at Usagi Electric and mentioned that this machine had this problem now and that I really was stuck because I have no idea how to reverse engineer 68,000 ROMs. And he suggested reaching out to people on his Discord server. Now, I alluded to this at the end of part 3 in the outro, and that's because I actually record that outro after I had already had that conversation with him. A little spoiler alert there. But what we decided on doing is creating a Discord channel on his server, because I don't have a Discord server, and asking people there if they could help with some of the analysis of the ROM code on this thing to give me the clues that I needed to figure out the hardware fault. So that's exactly what we did. We created a new channel. I put a note on my Patreon to have anyone come over from there who was good at this kind of stuff. And then he's already got a ton of people on his Discord server that are good at this sort of thing. And I went in there and I asked the question, hey, we have a machine here that is failing its diagnostics. And I really could use some help to figure out what it's doing when it fails. So I uploaded the ROM code that I had dumped from part 1, and people got to work in Ghidra and started analyzing the ROMs. Now, parallel to that, I have the hard drive image that I took from this machine in part 1 as well. And I've had a few people ask why I haven't posted the image online yet. I posted the ROM code and anything else that I found about this machine online, but not the hard drive image. Well, the reason why is I asked a few people to start looking at the hard drive image that I took with the emulator. I wanted them to start looking for anything that looked like PII or personally identifiable information on there. I don't want to have people's names and addresses, especially if this was a business computer used in operation of a business. It could have people's social security numbers, it could have addresses, names, all sorts of things. And I don't want to just go and upload that to the internet. That is completely irresponsible of me. And because the computer had failed, I could no longer look around the hard drive myself to try to see if the information was there. I didn't get a chance before this thing broke. So in parallel to everyone on Discord starting to reverse engineer the ROMs, I had trusted friends starting to look at the hard drive. And boy, did we find some interesting stuff on the hard drive. So I've printed out some stuff here, just some notes for myself, so I can try to keep all of this straight, because a lot of this was all happening in parallel on Discord and offline with the hard drive analysis. So for the hard drive, it did appear, and you saw this in part 3, that it looked like there were a few different user accounts on this machine. And what I didn't really get to, it looked like there was some kind of an Office suite on here, like a word processor type thing installed. And almost certainly this was just used for that type of activity. But what's really interesting is that the folks who were doing this analysis actually came to the discovery that there seemed to have been some other stuff on this machine that actually pertained to technical documentation for the computer itself. But the strange thing is it wasn't on any of the partitions that I saw in part 3. In part 3, the system booted up and there was the root partition and there was a /user partition. It appears there's also a third partition on the hard drive that is almost like a system restore. It's like a virgin copy of the operating system that was called, I think, /stock_u. That did not get mounted when I booted the system up, but it was there at the end of the hard drive. When the folks analyzing the hard drive started to use forensic type tools on it to look in what was ostensibly the free space on there, we started to actually find other documents. To make a long story short about accessing this data, and don't worry, I'll post a longer, more in-depth analysis of how it worked once we're able to clean up the data on the hard drive, sanitize it, get rid of the PII, stuff like that. What happened was, it seemed at some point, this computer was being used by someone who actually worked at Plexus. And the funny thing is, it seems the computer was repurposed for, civilian use, let's just call it. I mean, it's not military, but, not company use. It was going to be used by someone outside of the company. I think the machine was end of life at that point, and they just wanted to reuse it. So what happened is that person went to repartition the hard drive to erase that /user partition that had all the documents and stuff from its original use and created a new one for its new life and its new purpose. Now here's where things get wild, and this is honestly a stroke of luck you would not believe. The user partition on this drive started I think at block 60,000. That was the original location of the original user partition on this machine. Well, the new partition that was created for this computer's new life in office work was actually created most likely by a typo at 66,000. I might be leaving off a trailing zero there, but either way, there was a typo. Instead of 1 6 and a bunch of zeros, there was 2 6s and a bunch of zeros. So the new user partition was created and formatted it and set up for its new life, and that's where people put their office files or whatever. That original partition, though, was still there. It was never erased, it was just repartitioned, and instead of erasing the original partition and formatting it, it was created at an offset. Now, when this system booted up in part 3, it was mounting the new user partition, the one at the 66000, a bunch of zeros, and not the original one without the 2 6s. So with some forensic tools and then some other fanciness with old source code from System 5 and stuff like that, the people working on the drive recovery were able to access the files that were contained in that original partition. And it seems about 80 to 90% of them were not overwritten. I guess it wasn't that a ton of data was ever stored on this, so when the new partition was created with that offset, it actually didn't affect most of the files in that original partition. And because the original partition still had a super block and all the parts that make up a Unix file system, it meant even the directory structure was intact. So we didn't just have file names, we had an actual directory structure. Now, I'm not ready to release all the files that were in that hidden partition because just like in that later user partition for this computer's new life, there was also PII in that first partition. But what we could ascertain is that this computer was actually owned or used by someone at Plexus involved in the design of this computer. It's completely mind-blowing. Honestly, when we started looking at this data, we could not believe what we were seeing. And the reason why I say that is because in this directory were technical documentations about this computer. There were the equations for the PAL chips. There were the net lists, that is that list of all the connections between every chip. There were parts lists. There were technical documents outlining the memory map, the register map, the functionality, like the basic functionality of this, all the pinouts of all the ports, including this one here from multibus, and there's a diagnostic port down here, and the SCSI, and everything. It was all in there. There was even documents in there talking about the modifications required for the prototype machines to make them work. And all these baud wires that are on here were described in technical documents because the person, I think, who was using this machine actually worked on troubleshooting the prototypes. And while I don't think this is a prototype because the serial number on the motherboard here is like 100 and something, it's almost certainly one of the early run boards, which is why it has all these baud wires that were done after work by this person who worked on the design and did the troubleshooting for it. So we had just struck a literal pot of gold when it comes to this machine. Now, if we could figure out what the ROMs were saying when it came to that error code, that could actually give me a clue as to where it is. And now that I understand, because we have these files that are just text files, mind you, we don't have like a PCB schematic in a graphical format. You have to remember this was in 1984, I think, when this was designed. But we now have all the information needed to go from one chip to every other chip on the board because it's all contained in these files. I cannot express enough how much of a lucky break this was. This was unfreaking believable that we went from a computer that essentially had no technical documentation of any kind, just like a couple page pamphlet just outlining at a very high level what it was, to now having pretty much everything that's necessary to recreate schematics for this thing with enough work, and even go as far as create an emulator for this. Since I have the equations for the PAL chips now, that deobfuscates all the logic that's contained within them, and we have all the memory maps and all the other stuff, and we obviously have the ROM code, and we have a working hard drive image that can boot the system. Emulation is actually possible. So back on the Discord channel, I shared some of the information that we found from the recovery of the hard drive, including the memory map and a lot of the registers. And registers, if you're not familiar, they're essentially, think of them as a bunch of switch settings, but they're, instead of being physical dip switches, they're inside a latch chip. And what that latch does is when you set it, those values that are set, those bits on or off, stay there. And later, what the system can do is you can query the switch settings, so you can go and read what's in that chip, but also those chips can take action on various components on the motherboard. So for instance, you could imagine there could be a soft switch. We'll call it a soft switch for, say, diagnostic mode. When you set that in the register, then that can affect a bunch of logic that could change the functionality of the board. Well, most computers, including this one, have a bunch of these registers, and they do all sorts of different things. And understanding what those do is extremely helpful when you're trying to look at the software. The ROM is going to boot up and it's going to change modes of operation of the motherboard and whatnot, and that's all going to happen within these registers. And in that technical documentation was exactly that. A list of the registers, the memory maps, all that stuff. It was an unbelievable stroke of good luck that really is just almost impossible to comprehend. How lucky we were was unfreaking believable. So, armed with the knowledge of what the registers did and what the memory map of this entire processor address space is, remember these processors can address 16 megabytes of memory. With that knowledge, over on Discord, the team using Ghidra to reverse engineer the ROMs were able to ascertain that that error code that I was getting when I boot this thing up, or I am still getting when I boot this up, is the fact that it is unable to see any RAM. Yes, it cannot talk to the RAM at all. It does some routine that tries to scan for the RAM and then test it. And when it scans for RAM, it finds nothing. It finds 0 RAM. To help validate that hypothesis of what's wrong, I took this machine apart. I didn't record this or anything, but I removed the RAM card from the system. And sure enough, that error code did not change at all. It was identical error code, and it happens in exactly the same amount of time. So I had a lead as to what's going on now. Now here's where things get a little bit more complicated. On home computers using the 68000, imagine like a Macintosh or an Amiga, there's no protected memory. That means that any process running on your processor can access any part of memory. It can erase RAM, it can do whatever it needs to. There's no protection where, say, the system OS can say, hey, this RAM is protected, don't write to this. Because if you do, you're gonna crash the computer. But obviously, when you're using a multi-user computer like this, that has multiple people logged in, you need a way to have private memory for each of the users so that you don't overwrite each other's RAM and you don't crash the system for everyone. Well, what happened on these early multi-user Unix systems that used processors like the 68000 or the 6810 that didn't have that memory mapping protection stuff built in is you had to implement your own memory mapper on the board itself in hardware. Now, later versions of the Motorola 68000, I think the 68020 or maybe the 68030, it had that built in. That capability was all built into the chip, and that's why you started getting virtual memory and things like that later. Intel processors are exactly the same, 8086 and the 286. I think the 286 had protected memory, but it wasn't until the 386 that you really got full virtual protected memory where the OS could configure the memory management unit to give you more memory than you actually had that was virtual memory, and also protect memory to have protected operating systems, things like that. And that's why Linux and Windows NT require a 386 minimum, because those need those memory management units that are built in the 386 and up to do all that protected memory stuff. And that's the same on 68,000 chips. A lot of the actual Unixes that run on these types of Motorola processors, like the ones on the Macintosh, require machines that have a memory management unit, either a separate chip or built in the processor. Well, 68,000 and 6810, it doesn't have that. So this computer has to implement a mapper in a bunch of logic on the motherboard, and that's exactly what all this SRAM is. When I was talking earlier about the constituent parts of the motherboard, that hypothesis was confirmed that this was for the mapper based on information that we saw within the technical documentation that was recovered from this hard drive. Now, for troubleshooting at a hardware level, what would be really essential is having schematics, because that is a visual representation of every connection, every net on the board that allows you to easily follow from one chip to another and make your way through the system to try to figure out where your hardware fault is, because clearly that's what we're dealing with right now. The RAM card's installed in the system, but the CPU cannot see it. Now, with more modern versions of PCB design programs, they can create these netlist text files that list out all these connections between all the chips and stuff like that. And you can take those files and re-import them and turn it back into a visual schematic, you know, with a bunch of work laying out the board and stuff like that. The problem is, this board was designed in around 1984, where we didn't have tools that we do these days. And it seems that the tool that was used to lay this out was called Kale. I might be mispronouncing that. I think it was a German PCB design piece of software that ran on the PDP-11, the DEC PDP-11. So those were the files that were left behind. And unfortunately, it seems like, at least initially, no one has been able to take those files and load them into, say, KiCad to turn this thing back into a schematic. One of the users on Discord was manually taking these netlists and looks like recreating the ICs in KiCad, but it was an entire manual process. Looking at the files, these text files, you got to cross-reference the parts list file versus the nets file, and then rebuilding the chips one by one. And obviously, once you've rebuilt everything, if you have all those nets labeled properly, all the chips can be reconnected pretty easily. This machine appears to have over 1,000 nets. And remember, the net is where one pin connects to several other chips. That is a net. You could just imagine it like a little net across the board. There are over 1,000 of those on this board. And all of that has to be recreated by hand, because it doesn't seem like there's at least a way right now to import those tools. So what I had to do to start reverse engineering how this was working is trying to think about some of the reasons why the main memory wasn't accessible by the CPUs. Now, my first thought was that the memory mapper, the MMU that's designing hardware on this, had a failure of it of some kind. And without that, the system wasn't going to operate. That the CPU needed to talk through the memory mapper in order for the RAM to be even reachable. The technical docs were not clear on exactly whether that was the case or not. It did say in there that you had to have the memory mapper enabled for the operating system to work, for normal operation of the system. But what wasn't clear is if the ROM diagnostic routine also relied on the mapper or not. So I went off the assumption that the mapper was going to be necessary, so I started looking into the logic of the mapper. Now, when we look at the technical docs for the system, there are signals in there like disable mapper in a register that lets you turn on and off the mapper. And I needed to go from the register and then start going backwards and figuring out what that does exactly. What physical effect does that have in the logic on here when you disable the mapper? Because we don't have finished schematics for the system, all we have is these text files. To do this reverse analysis, I basically had to do it on paper. Now, I did it in Notepad, or Google Docs actually. And what I would do is I would go to the first chip that was the register for that disable map signal, and I would have to lay out every pin on that chip, and I think it was a 373 latch somewhere around here on the motherboard. And I'd have to go in the net list and find every other chip that the disable map signal goes to. And once I found each of those chips, I had to go and identify off the parts list what kind of a chip it was. And then I needed to figure out if the signals on that net were going into those chips or coming out of those chips. Because remember, every chip has an input and an output pin, and some of them have both. If it's a transceiver chip, it can actually change direction. So first, identifying every chip of what they are, going and looking up the pin out or the data sheet for those chips, figuring out if that pin that's identified on the net list is an input or output, so marking that. And that allows me to kind of figure out the flow a lot of times a signal will come out of one chip on a net and it will go into a whole bunch of other chips. And then from there, you have to look at all those other chips and see where they go and what they do and follow that path all the way through to the logical conclusion. I could see that the disable map signal in the register ends up in one of the PAL chips as an enable map signal, which has to do with turning on the entire mapper circuitry or turning it off. And I needed to make sure that when that register was being set high or low, that the signal making its way all the way to the PAL circuitry that turns on or off the mapper was working correctly. You can imagine that the ROM code might be telling that register, hey, disable the map and then turn it back on. And I could go to that PAL chip now having analyzed the entire flow of the signal through all the chips. And I could say, oh, I know now that when that disable signal on the latch is high and these other situations are met, the signal on the PAL chip should be low. And if it's not, like it's high all the time, even though the signal over on the latch is changing, then I know there's a fault in there. And using the information that I reverse engineered, I could then go try to figure out where exactly that fault is. Now, having worked through the entire map logic all the way through to the end where the PAL chip actually turns it on or off, I was able to conclude that that whole circuit was working perfectly. As designed, when the system starts up, the disable map signal is low, meaning it's enabled, actually. And what the ROMs do during the diagnostic process, they seem to activate that disable map signal in the register, which then actually does turn off the memory mapper. And I guess that's just done so the processor maybe can talk directly to the DRAM without the mapper circuitry being in the middle. And when you look at the diagnostic test that can run on this system, there is a test that runs later that's called mapper. And there must be some test routines that then exercise the mapper to make sure that it's functioning properly. And this is all before the system can boot the OS. So it seemed that the memory mapper circuitry on this was working properly, and then that was not the problem. That had nothing to do with why the CPU couldn't talk to the memory. So where to look next? Well, I wanted to start looking at the memory card itself. Now, it's difficult to troubleshoot because the board needs to be installed in here because the power supply cable is short and the RAM card is on the back. So I can't easily poke around on the RAM chips. That's where the Discord user Super SVGA came in clutch. I don't use that word very often because I'm, not hip with the young people. Basically, that user took all the information in the net list and recreated this 96-pin connector here in, well, a visual diagram that listed every single net for every single pin on here. I could probe around here with my oscilloscope, but not knowing what each pin did, I didn't really know what I was looking at. Well, with this map right here that Super SVGA created, I was able just to methodically go through all 96 pins and I wrote down exactly what I saw. And that would allow me to later go back and do analysis on, well, what these signals were to then figure out what seemed wrong. The gist of what I found on this connector is it has two data buses. One 16-bit data bus goes to this processor, which is the DMA processor. Now, DMA normally stands for direct memory access. I don't know what it stands for in this case. Maybe that's what it stands for as well. But nonetheless, this processor is the one that runs the diagnostic code, has access to all the I/O. It's what's active when you first turn this computer on. This other processor is called the job processor. And at this stage in the diagnostics, the people who reverse engineer the ROMs could see this processor is not doing anything at all. It's completely inactive at this point. So looking at the two data buses that were on here, I could see that the data bus that goes to this chip was busy. It had lots of normal activity on it, all 16 lines, but the job processor data bus, there was nothing happening whatsoever. And that was completely expected and is exactly what I thought I would see. Now, the other types of signals that you see going to the RAM card are address lines. Now, there are not two sets of address lines, only one set of address lines that goes to the RAM card. So obviously, because both processors can obviously talk to the RAM, there's logic on here to switch between the two processors. And when I went through all the address lines on here, there was no activity at all, none. So of course, with no activity on the address lines, A, you're not going to have any DRAM refresh, so the RAM can't even work. But then worse than that, clearly without address line activity, the processor is not going to be able to read or write from the RAM at all. Nothing is going to work. And most of the RAM signals were either low all the time, or some of them were just high all the time. And occasionally some of them were pulsing, I think with the reset signal. And I was using the Arduino to reset this thing. So that is a huge smoking gun for a problem. There's no way a system can work with no address line activity at the DRAM. And that's obviously why the RAM test was failing. Hey, I can't find RAM. Well, yeah, because there's no address line activity going to the RAM. And that brought me to the next phase of the diagnostic process. And it was exactly the same as I described with the map, going backwards through the signals. I picked some random nets on the RAM card connector here, various address lines, and I started going backwards to see how they work exactly. And I noticed a few things. The lower address lines, 0 through 11, they're only connected to a multiplexer, and the multiplexer seems to select between either of the two processors. The higher address lines, on the other hand, go through the memory mapper circuitry here, and the memory mapper circuitry is allowing, I think, 4 kilobyte pages of memory. So the minimum page size is 4K. And that means that the SRAM down here contains a map of all the memory that the processors can use to move memory around and create virtual memory and stuff like that. And yeah, 4K is the minimum size. So I decided to ignore the mapper circuitry and just focus on those lower address lines that go to the multiplexers, because even those lines, according to the oscilloscope that I hooked up to the pins here, those lines were just always low all the time. So clearly something was wrong. So I started reversing all those signals and just going backwards through everything. And I found the multiplexer goes through several different ICs along the way, and it goes through a PAL chip even that has to do with enable DMA, an enable DMA signal. And remember, DMA is this processor here. This signal obviously is used to allow this processor to communicate to the RAM. And I guess what happens is it gets turned off and on as the RAM access happens, where it allows the job processor, when it's running, to also talk to the RAM, you know, odd cycles or whatever. It switches back and forth, I guess. So when I took a look at the enable DMA signal on that multiplexer, this is the one that selects between the two processors, I could see that that signal was not changing. And that would mean in the idle state that that chip was in, when the machine was on, is that the RAM would always be connected to the job processor. It would never be connected to this one. Well, that's clearly not right. I don't know how that should look while the system is operating, but I know enough to know that when you look at the logic and the truth tables for the multiplexer, in the way it was here, it was never going to be able to talk to this because the enable DMA signal was never being set. So it was just a matter of going backwards through all the nets and all the chips that generate that signal. The enable DMA signal came from a PAL chip. I think it was this one right here. Has a bodge wire on it, but all the connections to that chip look good. And looking around at that chip with the oscilloscope and mapping it all out on the list here, everything else that was going on that PAL looked correct, but it looked like some of the signals that go into the PAL that have to do with selecting or deselecting the DMA functionality of the RAM, those weren't changing either. So the problem was upstream from this PAL. If the PAL were bad, and keep in mind, I didn't know at the time that we had the equations for this PAL, so I thought, uh-oh, if this chip is bad, we're completely screwed. But the reality is I could recreate this now because I think we have the equations for it. By the time I didn't know. So anyways, it looked like the PAL was still working, and it was the input signals into the PAL that were actually bad. So I just kept going backwards. And after going through some more chips, what that led me to was a flip-flop. And the flip-flop, which incidentally is right here, under where the battery is, that flip-flop is supposed to be generating a signal that tells the PAL chip to enable the DMA, and it looks like that signal wasn't working correctly. In fact, on the oscilloscope, I could see that there was a little bit of it trying to go down to ground, but it was just stuck around 5 volts. It was like going down a little bit, but not working. Now, one of the things about flip-flops is that there are 2 flip-flop units in one chip. So there's 2 separate sets of functionality happening. The other half of that chip working perfectly. You could see everything going swimmingly and working well. But the other thing about the flip-flops in here is there are 2 outputs, and one's an inverted output from the other. Well, one of the outputs goes to the PAL, and the other one goes to some other stuff on the board. And the one that was inverted and going to other stuff on the board, it was working. I could see it, you know, pulsing and looking normal. And it sort of was going in these bursts, which I guess are the enabled DMA signal. But the one going to the PAL chip, and it only went to the PAL chip, it was not working. It was just only slightly going down. It looked suspect. In absence of knowing the critical function of the flip-flop going down to 0 volts to enable the DMA processor and stuff, I don't know if I would have thought that that was a bad signal. It looked slightly suspect, but not really, because TTL can be kind of noisy at the top and the bottom. That's normal. That doesn't break operation of a system. And as I said, the inverted output of this flip-flop going to other things was working. That meant that the inputs that are going to the flip-flop are fine. Those whatever signals that go into it are actually good, because those 2 outputs of the flip-flop, they're just inverted of each other, but they need to always mirror each other. There's no way that they would ever be different than each other other than one being the opposite signal. So with that flip-flop looking like it was the smoking gun, The thing I could do to try to validate that the flip-flop is the bad part and not the PAL chip is actually take the PAL chip out of the socket, because it's in the socket, and lift the pin on the PAL that is going to the flip-flop. And according to the net diagram in the documentation we uncovered, there are only two things connected to that output of the flip-flop. Well, one thing really. It's the flip-flop itself and the PAL. That's it. It doesn't go anywhere else on the board. So when I lifted pin 3 on the PAL, and then I probed the flip-flop for that output, it still was screwed up in exactly the same way. No difference. So it was not the PAL chip that's forcing that output to be held at 5 volts. It was without a doubt the flip-flop. And to recap, the flip-flop generates a signal based on some other signals that tells the PAL chip that the DMA circuitry should be enabled for the RAM access from the DMA CPU. And because that signal was never going down to ground, the PAL never thought to turn on the access from the DMA processor to the RAM, which means that the processor had no way to ever talk to the RAM, and none of the address lines here would ever do anything because the job processor is not running at this phase of the diagnostic, thanks to everyone on Discord, we know that. And that's why I saw no access here, and that's why the processor had no ability to talk to the RAM. So that catches us up to where we are now. I didn't record any of this troubleshooting process, unfortunately, because I don't know, I just didn't know where I was going with this, and I didn't know if this was going to be, 5 hours of work or 500 hours of work. And it's very difficult to take 500 hours of footage and turn it into something. So that's why I'm giving a little bit of a recap now with the story of how I got to this point. The flip-flop is still installed in the board. I haven't done any further repairs at this point, so the board is still just as broken as it was at the end of part 3. But what we're left with now is actually time to take the flip-flop out of the board. I have another one. I found another one. It's a 74S112. I also found some LS parts, but the S parts are faster. I found one of my spare parts. We need to stick it in there and see if this fixes the problem. So let's go back to real-time troubleshooting. I'll get the motherboard out of here, and we'll get this chip out of here, and we'll see what happens. All right, the motherboard is on the bench, and since it was over in that computer, you may notice I actually added one extra bodge wire right here, and that is the reset signal that comes from the switch. The switch grounds the reset line that used to go to pin 2 on the power supply connector, but I cut a trace right there. I drew an arrow so I could tell where that was. I cut a trace right there, and then I connected the bodge wire over here to the AT Tiny so that the reset switch is connected to that, which means I can either engage the continual reboot mode, or if I change the code, it will just reset the computer. And if I put it back to run, it'll just continue to work. What we're here to work on though is the flip-flop, which is this one right here underneath the battery damage area. Now I alluded to the fact that I wasn't surprised once I figured out that this was the chip responsible for generating that signal, and it has gone faulty. Because originally the battery corrosion, you can see a little bit left on that connector right there. It had dripped down onto this chip, and a couple of the pins over here on the right top side were crusty. Anytime there are crusties around one chip, be very suspicious that that could be faulty. And I probably could have saved myself a little bit of effort if I went to this chip and I went to every pin on the oscilloscope and just looked at it. There was another one over here. I think this chip also is a bit crusty. This Motorola part here, it's a little bit of leftover hot glue there. So checking everything on here might be a good idea as well. There's still a little bit of crustiness around here from that battery leakage. It didn't seem so bad, but obviously it did cause some damage because, well, this chip failed. Of course, we don't know for sure if this is the only fault on this board right now, but it stands to reason that it is the one, because it's definitely a signal that's related to what's wrong with this board, and it's not working. Now, it stands to reason that that chip might not be the only one that's bad on this board, although it was working fine, and then of course it died, and well, we have a fault and we identified it for sure. It's happening on that chip. So I'm gonna pull it out, we'll socket it, and I went into my parts bin and I found these replacement chips right here. The top one being an exact drop-in, an SN74S112N, and these two are also the flip-flops, but they are the LS parts. So of course I'll start with this one here. I do know that these two work, these lower two, but this one's untested. Looks like it's never been in a computer though, or at least it's just been in a socket. So hopefully it's a good part. So this board has obviously a very thick flood fill for both ground and 5 volts all over the PCB. It's one of the ways this thing can run so fast is because it has all that grounding in there. That means that desoldering stuff is going to be extra difficult. So I'm going to use hot air to heat up the board while I use the desoldering iron at the same time. And that's going to help get everything out of here. All right, the socket is installed. Let's make sure we don't have any shorts. All right, those two are shorted. Not sure if that's on purpose or not. I'll have to go compare to the nets. The traces are very close to the pins. So you do have to be pretty careful with these vias that are here. Okay, I think everything is okay except for those 2 pins. Let's flip it over. All right, from the top side, it is these 2 pins that are shorted. Going to my notes, here's the flip-flop, and yep, 14 and 15 are both hooked up to PU7. It's a pull-up resistor, I guess, or a pull-down resistor or something like that. So just double checking that that's those 2 pins, and that looks good. This is the chip that I removed from the board. You can see a little evidence of the crusties that were right there, and it looks like it's crusty on the other side as well, at least on the underside. You can kind of see it's a bit crusty there. So we'll just straighten the legs on the new part that's going in. In goes the new chip into the socket. Compared to the old part, looks similar, although 323B on the old one and 332B on the new one, plus a yellow dot. And now it is time to reinstall this large motherboard into the computer, and let's see if it works. And this is the putty terminal I was using before. Now I found with this particular computer, if I let it go to sleep and then I wake it up again, sometimes it doesn't work, even though we're on COM 2 here, so a physical COM port. So I'm just gonna restart putty, because I would like to make sure that as soon as this starts to boot, we see exactly what's happening. All right, I have the camera positioned so you can see the LEDs. We can see if it goes into the failure mode. Here we go. Came out of reset, that's a good thing. Oh, we got Plexus on there. Here we go, everyone. It's about to fail if it's gonna fail. And the original test took way longer. Oh, this is good. This is freaking good. Here's the bad chip right here. Yeah, this would have failed by now. It would have had the error 4F02. I have like nightmares of that error code. I think this thing is gonna work again. Now, hard drive's not connected, SCSI's not connected, the power's unplugged from everything. So if this thing gets to the actual, oh no, oh no. This might not be a problem. Let me grab the keyboard here. I know if I hit the exclamation point, yes, you can exit out of this. This is stuff that the people on the Discord server figured out. So we're actually at like the boot prompt. Okay, well, it's trying to access the SCSI device and that's not there. So even though we had a clock failed and multi-bus failure, I think those are not critical errors. At least they're not critical like the RAM error was, because when I push exclamation point to exit out of the boot sequence there, what would happen is it would just immediately fail again because the system needs main memory for this thing to operate. And I don't think multi-bus and the clock working are that big a deal. And we have seen those errors before and they're sort of transient. Let me try to see if the reset works, the extra wire that I ran to the AT Tiny. So turn it to reset. Yes, it works. It went to reset. Turn it out to reset. There it goes. That's cool. That actually works. Yeah, the code that's currently on the AT Tiny is actually just normal code, meaning when you turn that to reset, it just resets the computer and it will fall out of reset as soon as you take the switch away from the reset position. So cool. We've replaced the whole power supply flaky reset circuit. Oh, config invalid. Yeah, I can exit out of this. The config invalid means that the clock chip itself is corrupted. There's no battery in here, so maybe that's that particular error that it's getting. I don't know. Okay, you know what? Let's plug the hard drive back into this thing and let's see if we can even boot this thing up. All right, I've reconnected the SCSI drive, the interposer, the tape drive, and the floppy drive. Let's turn this thing back on. Now, in case you're wondering about the multibus error, in part, I think it was part 2, we saw those same errors. They were sort of transient, although they seem to be, well, happening repeatedly here now. In part 3, I actually booted up without any error codes whatsoever. No clock error, no multibus, and we booted up into Unix. So the fact that the multibus card cage is not installed on the front of the machine, I don't think is actually a problem. So we might be dealing with another fault. Maybe there's some select logic issues or whatever that's happening on here. And yeah, we're getting those errors again. All right, self-test failed. Hit exclamation point to bypass. And that is it. It's booting. Yep, hard drive LED is blinking. So we are back in business, everyone. We are back in freaking business, I hope. Let's just see if this thing actually works though. Maybe those other 2 errors are actually so serious. Hey, I just realized, well, it is booting. It does say 2 megs of RAM. So before, when we weren't getting any error messages, it did actually show us how much RAM we had. It had some other information that did print, but now it doesn't print and I have to break out of the self-test with the exclamation point command. Is it frozen right now? Unfortunately, it looks like it is, everyone. Oh no. Yeah, we are stuck now. I'm pretty sure it booted more quickly than this. It got from the memory area here into the OS. It was like mounting the drives and stuff like that. And now it's just sitting here and doing absolutely nothing. Kind of has me wondering if the Unix operating system is trying to talk to, say, the clock, and I'm assuming it means the clock chip, and it's not able to, and that's why it's hanging here. As far as the multibus failure, well, I couldn't even explain why that is. I'm going to give a push to some of the socketed chips on the motherboard, like the PAL chips, because a few of them I've sort of jostled since I've been working on this thing, and give this thing a few reboots and see if I can get this thing booted. Well, unfortunately, I did a whole bunch of poking around, sort of fiddling with the board a little bit. Even put the multi-bus card cage thing back in there. Didn't make a difference. This thing is still unhappy. Now, I don't feel despondent like I did at the end of the last part, because at least now we have technical documentation, all those net lists, all that information that I need to keep troubleshooting this computer. At least we're much further along than we were. We're getting working memory. It's actually trying to boot the OS, but it's hanging up. And my guess is it's hanging up on the clock. That error about the clock is probably the clock chip. And since that's up in the battery damage area, I'm going to have to do some investigation. So this is going to continue into part 5. I might take a little bit of a break from the machine, work on some other stuff. Also let people catch up with watching the videos. There's people in the Discord channel who don't know what I'm talking about, because of course the only video that's gone live at the time of making of this video is the very first part. Meanwhile, the second part's available to patrons, but not everyone's a patron, so there's a whole lot of people who are operating in the dark, and it'd be nice if there was a little bit more of a catch up for the folks who are looking into the problems and troubleshooting this machine with me. So I really want to thank everyone who's helped me out, all the folks in the Discord channel who contributed to helping me troubleshoot this thing. And then a huge thanks goes out to the folks who were doing the drive recovery, because without that, we would have been so lost. We might have figured out that it was a RAM error, but troubleshooting the motherboard on this thing would have taken so much more work than it is now, because we have all that technical information that got recovered off it. How amazing and lucky was that this thing happens to have the information on it about the design of itself. It's almost like an inception or something like that. Anyhow, I think that's going to be it for this video. If you enjoyed it, I would really appreciate a huge thumbs up. If you didn't, you know what to do. Huge thanks to my patrons. Their names are scrolled on the side of the screen. They get early access to videos and other behind the scenes stuff like that. And I mean, I don't know, subscribe, all that other stuff. And I mean, I really hope you're enjoying this series on the Plexus P20. I am loving it. It is so fun to kind of uncover all the little hidden secrets of this long lost machine. So that's going to be that. So stay healthy, stay safe, and I'll see you next time. Bye.